So without further ado, we leave the mic to you.
Thank you very much for the introduction, and thank you very much for the invitation. I'm very honored to speak today to the Budapest Symposium. I hope that I pronounce that correct. So before we start, since there's quite some distance between you guys and the Netherlands where I work, I want to give you a brief cursory introduction about the place where I work. So I work in the Netherlands, somewhere across the pond, and the Netherlands, what it's known for tasteless cheese, for windmills, for tulips, and notorious leisure time activities. And in the Netherlands, more exactly, I work in Utrecht. That's a small town, half an hour away from Amsterdam. And in Utrecht, we host one of the world's most powerful NMR facilities. So we have a 900, 700, 800, a 400, and a 600, and even a 1,200 megahertz magnet. This is actually the best stable magnet in the world. And this is only one of our 2 NMR holes. So we have another one that holds 4 more magnets. And then for specialists, so these magnets, like the 400 and the 800, they're also equipped with hyperpolarization techniques such as dynamic nuclear polarization. And the great thing is that this facility is actually accessible to groups worldwide. So if you today see some things that you feel could align with your research, you can actually apply for measurement time via these European funding organizations, INEX Discovery, Instruct ERIC, and exceptionally this year, access is also free of charge for groups from everywhere over the world. So if you find something interesting, don't hesitate to apply for measurement time in Utrecht. So in this setting, I think that we don't need any introduction, right? So all you guys, as far as I understand, work on peptides against viruses or bacteria, fungi, whatever. So I will skip the introduction and go directly into the matter. So the research focus of my group is antibiotics, and I will now show some of our targets. So we work on antibiotics, mostly peptide antibiotics, but not only peptide antibiotics that target the ribosome. This is a project that we started recently in collaboration with Pete Dedon from MIT. We also work on antibiotics that target outer membrane proteins, especially the essential outer membrane proteins, BAMA and LPD. And we also, and that's our major research line, we work on antibiotics that target lipid-2. With lipid-2, so it's much smaller than the ribosome or an outer membrane protein. So what is this? Our major target, lipid-2. So lipid-2 is also known as the Achilles heel of bacteria, and it is a precursor molecule of the peptidoglycan network. And you see here, oops, let me just check. You see here, can you see the laser or my cursor? Can somebody please confirm this? Can you see the cursor? Yes, great, thank you.
Yeah, you can see the red light.
Yeah, okay, thank you. So, so you see here an illustration of the peptidoglycan. I'm sure that all of you are familiar with this. The peptidoglycan is essential for bacteria as they die without it. And peptidoglycan is composed, as all of you know, of repetitive sugars in blue that are tied together by a short pentapeptide bridges in yellow. And peptidoglycan is in constant turnover, and it's tied together via, or it is built from its precursor lipid-2. You see here an illustration of lipid-2. Lipid-2 is built from a pentapeptide, sugars, pyrophosphate group, and a complex lipid type. And lipid-2 is assembled in the cytoplasm and then flipped across the blood membrane, where the head group is chopped off and integrated in the peptidoglycan, and the rest is cycled back for the next round. This cycle is essential for bacteria. Any drug that interferes with it is an antibiotic. And this notion was famously validated by vancomycin. I'm sure that all of you know vancomycin. Vancomycin used to be an antibiotic of last resort, and it binds here at the lipid-2 pentapeptide. All of you know peptides can be mutated. That's why many bacterial strains are resistant to vancomycin these days. So we work on antibiotics that have a smarter binding mode. That bind here at the pyrophosphate. And since phosphates cannot be mutated, this binding mode is alpha robust to the development of antimicrobial resistance. And it's also very powerful. For instance, a few years ago, tioxibactam was discovered, which is an extraordinarily powerful antibiotic. And it also targets lipid-2, and there are many other flashy or antibiotics that target lipid-2 that were published in flashy journals, for example, Plexus, published in Science in 2010, or malacidin, which was relatively recently discovered, which also binds to lipid-2. Now, today I will show you our research on tixobactin and also later on Plexus. The major problem is that the binding modes of these lipid-2 binding antibiotics are very poorly understood. There are virtually no high-resolution data available and no data at all in physiologically relevant membranes. And this scarcity of relevant high-resolution data is a major limitation for the use of these powerful compounds to develop next-generation antibiotics. And our ambition is to change this. So we want to understand these drugs at high resolution and directly in the physiologically relevant membrane environment. And I want to give you one succinct example why we need to understand membrane-active drugs in membranes. So this here is niacin, and I'm sure that many of you are familiar with niacin. So niacin is a poster child of the lipid-2 binding peptide antibiotics. And niacin is a so-called antibiotic, and it features 5 signature tioeserins that adapt A, B, C, D, E. And it's well known that rings A and B target the pyrophosphate of lipid-2, and there is already a really famous structure of the niacin lipid-2 interaction available that was solved in mice cells using solution NMR. You have here the original solution NMR spectrum in mice cells from the NSMB paper that shows niacin bound to lipid-2 in mice cells. So let's see what happens if we measure exactly the same complex in physiologically relevant membranes. You see, that's a difference like day and night. The spectra are completely different. And this must mean that the complex is also completely different in biological membranes. So this means if you want to understand membrane-active antibiotics, you better do it in membranes. Who would have thought this? So this is something that we published 3 years ago, and we have meanwhile progressed a lot on this. So we have solved the structure of the lipid-2 niacin interaction, and that's something that we are now wrapping up in a comprehensive paper that will be quite controversial, I assume. But today I'm not going to dwell on niacin any longer, but instead I'm really excited to show you our recent work on tixobactin. I have 2 stories on tixobactin to share. So what is tixobactin? So tixobactin was discovered 6 years ago in a truly spectacular paper by the group of Kim Lewis from Northeastern University. Tixobactin made a buzz worldwide. It was globally heralded as wonder drug, as a game changer in the combat against multi-drug resistant bacteria. And tixobactin has a real perspective. Clinical trials are supposed to start next year. So, but what is tixobactin exactly? Tixobactin is an 11 residue peptide that features many unnatural amino acids, including 4D amino acids here, there, and there. And it also features a C-terminal ring structure. In this ring structure, we have a very unusual amino acid called L-allo-N-giracidine that was only encountered 3 times in nature. In this original paper, it was also shown that tixobactin targets lipid-2. So what else was known on tixobactin? It was known that somehow the N-terminus is essential for activity. If you chop it off, you lose all activity. It was also known that you cannot tamper with the order of DNL amino acids. If you change the order of DNL amino acids, you lose all activity. Likewise, if you change the order of hydrophilic and hydrophobic amino acids, you also lose all activity. So a lot was already known before we started, but there was no information available in membranes, and that's what we wanted to contribute. So initially, unfortunately, we could not work on natural tixobactin, and that's because natural tixobactin is produced in a so-called unculturable bacterium, Eleftheria terrae, which means freed from earth. It's a soil bacterium, so you cannot simply culture this in your lab. And you also cannot simply isotope label natural tixobactin. It's very, very expensive, and that's because of the presence of this funky residue, L-allo-N-giracidine. That's why we teamed up with Ishwar Singh from Liverpool University. So Ishwar showed that if you replace this funky residue, L-allo-N-giracidine, by a leucine, you preserve a lot of the activity, and the cost of synthesis is reduced by 4 orders of magnitude. So for the first part of our tixobactin research, we used these tixobactin analogs. In order to make these analogs amenable to solid state NMR studies, we needed to introduce carbon 13 and nitrogen 15 labeled amino acids. So we labeled 6 of the L amino acids that covered the entire molecule. This here is already the complex with lipid 2 in liposomes, and we count 1, 2, 3, 4, 5, 6 signals that correspond to the 6 labeled amino acids. So every signal that you see here corresponds to 1 labeled residue. And we can readily confirm that this is a complex. First, it looks totally different at the free state, and second, we also can demonstrate that it binds to the pyrophosphate of lipid 2. These here are phosphorus NMR studies in liposomes. So the liposomes were doped with lipid 2. And here this is a free state without tioxobactin. These 2 signals relate to the 2 phosphate groups of the pyrophosphate. And once we add tioxobactin, we see a strong chemical shift perturbation that clearly demonstrates complex formation. So first, we wondered about the secondary structure of tioxobactin in the complex. Therefore, we acquired this beautifully resolved 2D carbon-carbon spectrum of tioxobactin in the complex. From the spectrum, we can readily determine the secondary structure. Therefore, we compare the experimental chemical shift to the random coil chemical shift. If this difference is positive, you have an alpha helix. If it's negative, you have a beta strand. And you readily see that the N-terminus adopts a beta strand in the bound state. So next, we looked at the oligomeric state, the supramolecular structure of tioxobactin in the complex. So therefore, you have here a superposition of solid state NMR spectrum that were acquired with a short mixing time. So this short mixing time means the time during which 2 carbons can talk with each other, and the long mixing time. So in blue, the carbons only talk to each other for a short time, and in magenta, the carbons talk to each other for a long time. And the longer the carbons talk to each other, the longer the distance that you can bridge. Yeah? So that means in the red spectrum, you can determine contacts between carbons that are further away. So you can probe longer distances. So in this spectral superposition, please ignore the signals with black and blue labels. They are not interesting. And please focus on the signals with red labels. These are the interesting long-range contacts. And we see here long-range contacts between residues 2 and 6 and even 2 and 7. Now, if you consider that the distance between C alpha and C alpha plus 2 in a beta strand is 6 angstrom, it means that the distance between residues 2 and 7 would be 15 angstrom. And this is absolutely impossible, because with solid state NMR, you can only probe distances around 7 to 8 angstrom. So you can only explain these distances if the transfer between residues 2 and 7 is intermolecular between antiparallel beta sheets. And we could clearly confirm this oligomerization of tioxobactin in the complex using fluorescence spectroscopy. Here we use pyrene-checked lipid 2. Once 2 pyrene molecules come close to each other, they yield a unique Oligomers signal at 490 nanometer. And this is exactly what we observed upon the addition of tioxobactin to pyrene-checked lipid 2. You have here the buildup of this Oligomers signal at 490 nanometer as a function of the tioxobactin concentration. So clearly these data demonstrate that tioxobactin oligomerizes upon lipid 2 binding. So next, we wanted to look into these oligomers at high resolution. First, we wanted to investigate if the Dempsey cycle of tioxobactin, so this is this ring structure here, if the C-terminal ring structure really targets the pyrophosphate of lipid 2. That was already strongly suggested in the literature, but there was no proof. In order to get this proof, we acquired a 2D protein phosphorus spectrum. Here we transfer magnetization from the amino proteins of tioxobactin to the pyrophosphate. This really worked out very well. So there is no transfer from the bulk lipids. This is a big signal of the bulk lipids. The phosphate is the bulk lipids, but there's transfer from the pyrophosphate. And in order to annotate the signals, in order to assign these signals, we can simply look at our HSQC spectrum. And we need to realize that these protein signals, or this protein dimension, is exactly the same as that protein dimension. And then we can transfer the assignments, and we see that these signals perfectly match with residues 9 and 10 of the Dempsey cycle. So the Dempsey cycle really targets a pyrophosphate. So next, we need to understand the role of the sugars in the pentapeptide in the complex. Especially the role of the pentapeptide is important, because it's here that bacteria can introduce many modifications. This is, for example, where the resistance of vancomycin comes from. For vancomycin resistance, these two this residue here is replaced from an alanine to a lactate. That's where vancomycin resistance comes from. So in order to understand with solid state NMR the role of the sugars in the pentapeptide, we had to carbon-13 label lipid 2. This was done by my previous PhD student, John Madeira Silver, who's now doing a postdoc in the group of Mei Hong at MIT, and my collaborator, Avian Brooking. And this worked like a charm. So you have here a carbon-carbon spectrum of lipid 2. These are the sugars, and that's the pentapeptide. And I will briefly show you on the example of niacin how we can use this to determine the interface. Here in magenta, you have a 2D carbon-carbon spectrum with unlabeled lipid 2, and in green you have a 2D carbon-carbon spectrum in which both niacin and lipid 2 are carbon-13 labeled, and many of these blue contacts that have no magenta correspondence provide us with precious information on the interface. So let's use this approach now to determine the interface between tiosurfactant and lipid 2. These here this is a superposition of 2D carbon-carbon spectra with carbon-labeled lipid 2. You can get high-quality information on the interface. Here we plotted all interfacial contacts on the primary structure of tiosurfactant, and you see that the interfacial contacts cluster at residues 9 and 10 of the Dempsey cycle. So the Dempsey cycle is really the complex interface. We see that almost all signals relate to the Myrmex sugar that is covalently attached to the pyrophosphate. So that means the Myrmex sugar is directly at the interface, while there are virtually no contacts for the second sugar, the gluconex sugar, which means that the gluconex sugar must be distal from the interface. And curiously, in this so-called dipolar spectrum, we did not observe any contacts for the pentapeptide. In this so-called dipolar spectrum, we only observe rigid residues. So the fact that we do not observe the pentapeptide strongly suggests that the pentapeptide is highly mobile in the complex and not directly involved in the interface. And we could unambiguously confirm this using a so-called scalar solid state NMR spectrum. In a scalar solid state NMR spectrum, we only observe highly mobile residues. So, and indeed, in this spectrum, we only observe the pentapeptide. Here, residues 5 and 4 of the pentapeptide. Here's residue 3, and that's residue 2 of the pentapeptide. So the pentapeptide is highly mobile and not at all involved in the interface. So let's put this all together. What have we learned so far? We have learned that the Dempsey cycle of tiosurfactant coordinates the pyrophosphate of lipid 2. The Myrmex sugar is directly at the interface. Gluconex is distal from the interface, and the pentapeptide is not at all involved in the interface. And that the pentapeptide plays no role for the complex formation is very important, because that means that tiosurfactant does not care about all the modifications that bacteria introduce into the pentapeptide, and that's one of the major reasons why tiosurfactant is so robust to the development of antimicrobial resistance. So, in order to solve the structure of the complex, we still missed one thing. We did not know the membrane topology. In order to determine the membrane topology, we used an old trick developed from the group of Mei Hong. It's a so-called mobility edited, or for the specialists, T2 edited solid state NMR experiment that we transfer magnetization from mobile lipid tails and mobile water to the rigid antibiotic. And we see that tiosurfactant talks to both the water and the lipids, and that's typical for a compound that sits at the water membrane interface. The only two exceptions here, the long isoleucine tails, the long hydrophobic isoleucine tails 2 and 6, they only talk to the lipids but not to the water, and that means that the isoleucines are partitioned into the membrane. Thereby we have determined the membrane topology, and we can determine the complex structure. Therefore we used the haddock approach. This is a docking approach that can be fed with experimental data, and that worked very well. We could determine the complex with high resolution. This here is a representative structure of the complex. In yellow, you have the antiparallel tiosurfactant beta sheet. You see that the Dempsey cycle tightly interacts with the pyrophosphate. Myrmex is directly at the interface. The gluconex sugar is distal from the interface, and the pentapeptide adopts random conformations and is not shown here. If you look into this more carefully, then surprisingly, we observe that there are actually no favorable interactions between this tiosurfactant analog with the leucine at position 10 instead of the endurositidine and the gluconex sugar. And you see here, this is all hydrophobic, and there are no favorable interactions between the sugars and tixobactin. So that means that we have a combination of a specific interaction between the Dempsey cycle and the pyrophosphate and the fuzzy interaction between the sugars and the tixobactin side chains. So, but what I really like most about the structure is that it enables us to understand the stereochemistry of tixobactin. In the structure, we have a clear-cut separation of the hydrophobic residues and the hydrophilic, the hydrophilic residues and the hydrophobic residues. Hydrophobic residues face the membrane, hydrophilic residues face the water. And you can only get this clear-cut separation with this stereochemistry of tixobactin. If you imagine it a hypothetical all L-tixobactin, you ended up with some residues, some hydrophobic residues that face the water and some hydrophilic residues that face the membrane. A favorable interaction can only be obtained with this stereochemistry. So this is what we learned from our structural studies on the tixobactin analog, and we were really thrilled with what we could squeeze out the structural studies. But there was one additional observation that we made that really confused us. So we knew from our NMR studies that tixobactin oligomerized upon complex formation, and we wondered if we could even observe a macroscopic signature of these oligomers. And therefore, we conducted fluorescence microscopy studies using MBD tag lipid 2. And you see here the uniform distribution of this MBD tag lipid 2 on the surface of a giant unilamellar vesicle, so on the surface of a limestone. And once we added tixobactin, we strikingly observed the formation of these massive micron-sized clusters. And that was a very surprising observation, but we had no idea at all what this meant. So was this an artifact? Had this any functional importance? We did not know. So at the end of our study, there were two major questions open. First, what is the role of these clusters here? And second, what is the role of this funky residue endurocytidine that was only observed 3 times in nature? So, and then a lot of good things happened. So on the same day when we published our study, I was contacted by Kim Lewis. I'm sure that many of you are familiar with Kim. So if it's Kim's name, so he's a discoverer of tixobactin. And together with the company Novobiotic, he's developing tixobactin towards clinical studies. So and together we decided that we would investigate the mode of action of tixobactin, of natural tixobactin in membranes, and soon after we got a few milligram of uniformly carbon and nitrogen labeled tixobactin. And as you can see from these solid state NMR data, natural tixobactin gives fantastic spectra in complex with lipid 2 and natural membranes. From these data, you can readily determine the structure. So in these data, we can also obtain clear information on the endurocytidine side chain, which is here, and also on the N-terminal D-phenylalanine, which is also very important for the binding mode, as you will see later. So long story short, natural tixobactin also forms antiparallel beta strands. You see that here from the secondary structure, and natural tixobactin also forms these oligomers. So next we investigated the interface between natural tixobactin and lipid 2. We have here a superposition of 2D carbon-carbon spectra, a zoom into the endurocytidine side chain, in red with unlabeled lipid 2, and in blue with carbon-13 labeled lipid 2. And from these data, you see that endurocytidine is very prominent at the interface. All these blue contacts without red correspondence mean interfacial contact. So if we summarize this and put all the interfacial contacts together on the primary structure of natural tixobactin, then we see that endurocytidine is very prominent at the interface with 11 unambiguous interfacial contacts. And this has consequences. And because some of these interfacial contacts, they are visible with a short magnetization transfer time. So if they are visible with a short magnetization transfer time, it means that the interface must be very tight. And this is also representative, or this is also visible, measurable by colorimetric studies, for which we used ITC experiments. So you have here a comparison of ITC experiments for natural tixobactin and cyan and the tixobactin leucine 10 analog in magenta. And first, you see that tixobactin has natural tixobactin has a much higher affinity for lipid 2. It's almost 10 times, the affinity is almost 10 times higher. And you also see that the enthalpy is much more favorable for natural tixobactin, means more favorable hydrogen bonds, more favorable electrostatics for natural tixobactin. So if we put this all together in a model, this means that the tixobactin analog has a fuzzy interaction with lipid 2 because the leucine 10 cannot favorably interact with the sugars, whereas natural tixobactin has a specific interaction with lipid 2 because here enduracytidine highly specifically interacts with the sugars. And this means that natural tixobactin is the better binder and most likely also the better drug, because a higher affinity and a higher specificity usually come along with less side effects and less toxicity. So this is the structure of the complex between natural tixobactin and lipid 2. It's very well defined. You see here 4 similar interfaces, and this is due to the high affinity of enduracytidine to lipid 2. If we look here into the interface, then we see again that the depsicycle tightly interacts with the pyrophosphate, and we see that enduracytidine electrostatically interacts as a cationic residue, electrostatically interacts with the pyrophosphate, and also specifically interacts with the Murnich sugar. And strikingly, we also see that the cationic N-terminus, which is N-methylphenylalanine, also directly interacts with the pyrophosphate, and this is in very good agreement with our experimental data. We also see a direct interaction between the N-terminus and lipid 2. And we conducted molecular dynamic simulations, and in these simulations also show that this dual interaction of 2 tixobactin molecules with lipid 2 is very important for complex stability. So these inner tixobactin molecules are much more stably, these inner lipid 2 molecules here in the oligomer are much more stably bound than these outer lipid 2 molecules. So this clearly demonstrates that oligomerization improves complex stability. So this is one of the reasons why oligomerization is essential for activity. There's another reason to which will come afterwards. So natural tixobactin also forms these clusters, and this time we made a striking observation. So we observed that these oligomers also deform, perturbs the membrane. This is even more visible in these bright field images. We also conducted static phosphorus NMR studies. These are standard experiments to gauge membrane perturbation, and you clearly see that the addition of tixobactin deforms the membranes. Together with James Norwick, who provided us with tixobactin analogs, we could also demonstrate that in these clusters, tixobactin and lipid 2 co-localize. This is no surprise. And we could also demonstrate that tixobactin forms clusters with lipid 2 in bacteria. You see here these little dots. Wait, we'll just change my cursor. You see here these little dots here, there, that all show tixobactin lipid 2 clusters in bacteria. So these phenomena really happen in vivo. These are not in vitro artifacts. So next, we wanted to understand the role of these clusters, and therefore we first conducted molecular dynamics studies. So these are molecular dynamics simulations, atomistic molecular dynamics simulations, using our solid state and mass structure as a starting structure. And there, strikingly, after a few hundred nanoseconds, we observed massive membrane perturbations, which perfectly align with these massive membrane perturbations that we observed in microscopy studies. So we wondered how these membrane perturbations come into place. And these membrane perturbations are induced by the highly hydrophobic underbelly of tixobactin that works like a wedge that's placed in the membrane. And even more importantly, in these massive clusters, we have a high local concentration of these lipid 2 tails. And these lipid 2 tails are strongly non-laminar. First, they're very long, as you can see, 55 carbons. and they are also highly unsaturated and branched. So these are strongly non-laminar lipids. And if you have a high concentration of these strongly non-laminar lipids, this will perturb your membrane. So next we wondered, hey, could these membrane perturbations even contribute to the killing mechanism of tixobactin? And yes, it does. So we conducted, or we performed membrane permeability studies in different bacterial strains, and for all bacterial strains, we observed that the membrane potential disappeared quickly after the addition of tixobactin. You observe this here. So this means that the membrane gets damaged, decisively damaged upon the addition of tixobactin. This means that tixobactin kills bacteria by a two-pronged mechanism. First, it inhibits the peptidoglycan synthesis, and second, it destroys the membrane. So this is really a novel binding mode and a paradigm shift how these lipid 2 binding antibiotics kill bacteria. And the great thing is that this membrane damage only happens in the presence of lipid 2, and mammalian membranes do not have lipid 2. So this only destroys the membranes of bacteria. This is now in review in Nature, and we're really excited about these data. I'd like to quickly thank my team. So the key players here are Francesco, who did the MD simulations, Mike, who did a lot of lipid 2 biochemistry, and Rizma did a lot. She did all the NMR studies and the calorimetric studies and much more. I also like to thank some of my collaborators without whom we couldn't do anything. So Erwin is our lipid 2 expert. Ishwa provided us with the tixobactin analog, and Kim is a great collaborator and provided us with natural tixobactin together with the company Novobiotic, and Moreno helped us with some of the phosphorus and NMR studies. And then I'm wondering, so I guess I'm running out of time. Otherwise, I could also show you for 10 minutes something on another antimicrobial peptide. That's up to you.
Okay.
Go ahead. Yeah, there's no problem for us.
Yeah. Okay. Thanks.
Thank you.
I'm not going to keep you for a lot of time. I'll try to rush through it. I will quickly speak on plexism. So this won't be very smooth. This is the first time that I'm going to talk on plexism. So I cobbled some slides together. I guess that many of you are familiar with plexism. So plexism was discovered already in 2005 by Novozymes, a company from Denmark. And it also made a big buzz back then. So what is plexism? So plexism is an antimicrobial peptide from fungi, from Pseudoplectania nigrella. And the name is very telling. So all these alpha-beta defensins, they have an alpha helix and a beta sheet, and they're very compact. They're held together by several disulfide bridges. And there are many of these alpha-beta defensins, and they all look alike. They all have an alpha helix and a beta sheet. And plexism has very favorable pharmacokinetical properties. It's non-toxic, and it's also active in animal models. So since all these alpha-beta defensins look alike, the assumption is that they all share the same mode of action. So if we understood how plexism worked, it could be interesting for an entire class of antibiotics. In 2010, again, Novozymes, a company from Denmark, showed that plexism binds to lipid 2. This is a landmark paper published in Science. And in this paper, they also came up with a mode of action. And that was derived in mice cells using solution animal. In this mice cell model, they showed that cysteine 37, which is here in the beta sheet, interacts with the pyrophosphate. And they also showed, backed up by biochemical data, that the pentapeptide of lipid 2, so you have a pentapeptide, interacts with plexism. So you have here a more detailed look into the pentapeptide, sorry, into interaction. You see here cysteine 37 forms a hydrogen bond with the pyrophosphate. Here you have the glutamate 2, of the pentapeptide that interact with the N-terminus of plexism. And then we have histidine 18 of plexism that's also involved in the interface. You don't need to recall all these details. I will come back to this. Histidine 18 will be very prominent in the slides that I'm going to show you. What made us wonder about this mode of action that was published in the science paper was that it's difficult to align this with a triple mutant NZ2114. So what is this? A triple mutant NZ2114. So when Novozymes, a company, discovered Plexusin, they actually did not follow up on the development of Plexusin. Why? Because Plexusin had no activity against MRSA, and for the company that was not economically viable to develop a narrowband antibiotic. So they did a tour de force, a major mutagenesis study, and in this mutagenesis study, they discovered a triple mutant called NZ214 that was active against against MRSA. And strikingly here, the residues that were identified in the Meisel model, that bind LIPD2, they do not coincide with the triple mutations in NZ214. And that made us wonder, and we decided to look into the mode of action of Plexusin in phospholipid membranes. Although, cut a long story short, so Plexusin in complex with lipid 2 gives fantastic data, a highly defined complex, and we also do observe the histidines. In the Meisler model, the histidines are actually not observed. So this here is purely based on modeling data, no experimental data at all involved. I will come to this approach, how to determine the complex afterwards. So
thank you, Max. No, go ahead.
Okay. And so we also confirmed that our Plexusin is active, so we get virtually exactly the same MIC data that they published in the Nature paper. And we also confirmed that our Plexusin binds to lipid 2. Here we have again phosphorus solid state NMR data with and without Plexusin. So without Plexusin, this here's a lipid 2 signal, and with Plexusin, then we have a prominent signal change, which means that Plexusin really binds to the pyrophosphate of lipid 2. So let's come to the mode of action that was determined in the science paper. So how did they come up with this? So that was done with solution NMR in mice cells, as I already mentioned. And these are really the original data from the science paper. And they made a very valid assumption, and they had a very rough approach. So they simply compared the chemical shift of Plexusin in mice cells with and without lipid 2. And these are the chemical shift perturbations. So for example, for these residues here, there were no chemical shift perturbations. And for cysteine 37, here, they observed major chemical shift perturbations. Cysteine 37 is here. So you see a major chemical shift perturbations. And from these data, you can clearly come to this conclusion, hey, cysteine 37 interacts with lipid 2. They had, however, no distances, so they had no contacts. They only had chemical shift perturbations, and that cysteine 37 then binds to the pyrophosphate. Now that comes from the modeling, right? So that's comes from the model. That's not really based on experimental data. So we did exactly the same, but this time not in mice cells, but in phospholipid membranes. And that's what you get in membranes. So that looks totally different. And from these data in physiologically relevant membranes, well, there's no reason to believe that cysteine 37 is a privileged binding site. It looks totally different, right? So next we look at the role of histidine 18. So why is histidine 18 so prominent? So in all these alpha beta defendants, and these are the most prominent alpha beta defendants that were published, they all have the same folds, this alpha beta defendant fold, but there is a strong sequence diversity. Only the glycines are conserved. You need the glycines to have very short loops, and the cysteines are conserved. You need them for the disulfide bridges. But otherwise, only histidine 18 is conserved. And people don't know why. And it's also critical for activity. If you mutate it, you lose the activity. So it was known from biochemical studies done by the group of Hans-Georg Saal and Tanja Schneider that the glutamate 2 is critical for Plexusin's activity. Glutamate is charged, of course. So, and then they simply came up with the conclusion that, hey, if the glutamate is important, then maybe this histidine is protonated, and in some of the docking studies, they observed that it interacts with the glutamate, and that was then published in Science without any experimental corroboration. The thing is, with solid state NMR, we can simply check if the histidine is protonated. It's very simple. So here we have the histidine the histidines of plexusin in the complex with lipid 2. If the histidine is protonated, then you get a big signal at 160 ppm and a big signal of equal intensity at 180 ppm. Well, there's nothing. If it's not protonated, then you get a small signal at 250 ppm. So unambiguously, the histidine is not protonated in the complex. So this here is just fantasy. It's just based on model. It's just modeling without any meaning. So also this second prominent feature of the science paper is not correct. So that's why we really wanted to revisit this mode of action in detail. So what is really striking is the role of the histidines and plexusin. Plexusin has two histidines that are diametrically opposed. So if one of these histidines is, according to the science paper, involved in lipid 2 binding, so what does the other histidine do? Both histidines are critical. If you mutate them, you lose all activity. That was shown by a Chinese research group, and we could confirm this. And we also produced these mutants and conducted colorimetric studies. So if you mutate histidine 18, you lose a factor of 10 in affinity. And if you mutate histidine 16, then you actually lose all affinity to lipid 2. There's no binding any longer. So we wondered, hey, if we have binding to lipid 2 by one of these histidines, what happens on the other side? We have seen from plexibactin that it oligomerize. So we wondered, hey, could plexusin also oligomerize? And yes, it does. Therefore, we conducted studies that we can call them animal threat studies. We mix nitrogen-labeled and carbon-labeled plexusin, and then we form the complex with lipid 2, and we transfer magnetization from nitrogen to carbon. This transfer only works if plexusin oligomerize. They need to be close, really like on the distance of 1 or 2 angstrom. This is much better than FRET because it's non-invasive. And so this clearly works out. So here we have the signal buildup of the nitrogen to carbon transfer in the complex. And in order to get false positives, we used a modern solid-state NMR approach called DNP-enhanced solid-state NMR, which works with very low lipid 2 concentrations that are physiological. And with this DNP approach, we can even acquire 2D spectra. In these 2D spectra, we clearly observe that one of these histidines, we cannot resolve which one, unfortunately, that one of these histidines is directly at the plexus and plexus interface. We also did microscopy studies. Unfortunately, I don't have the data here, but we also did microscopy studies that clearly show that plexusin forms macroscopic clusters in the presence of lipid 2, exactly the same as plexibactin. And this also explains the prominent so-called post-antibiotic effect that plexusin has. Post-antibiotic effect means that hours after the addition of the drug is still bound to bacteria at sub-MIC values, and that's because these complexes, they form irreversible and they're not cleared from the body or from the organism. So, and we also conducted titration studies in order to determine the stoichiometry. So if you have stoichiometric ratios like 0.5 molar, 0.5 mole of plexusin, 1 mole of lipid 2, then the complex is relatively mobile. This is done with a solid state NMR. If you have equimolar ratios, then the complex get much more rigid, but this rigidity doesn't change if you add more plexusin. So this strongly suggests that we have a 1-to-1 stoichiometry. We also looked at the interface, again, using carbon-13 labeled lipid 2. Here in red, we have unlabeled lipid 2. In blue, we have carbon-13 labeled lipid 2. All these blue contacts without red correspondence tell us on the interface. So we see that all the tyrosines are at the interface. That makes sense because they're all clustered together. And also, if we knock out these tyrosines here, then we lose actually all activity for tyrosine 40. We know that tyrosine 14 interacts with the pentapeptide, and also here tyrosine 29, tyrosine 25 really strongly affects the interface. So that all makes sense. We also see that NZ, I will have 2 slides on NZ afterwards, really is much more active against than plexusin against MRSA. So long story short, this is the interface. We're still working on the interface. I'm not going into details. This is yet to be refined. So just 2 more slides on NZ. So NZ is active against MRSA while plexusin is not active against MRSA. So there is absolutely no molecular explanation for this. It's just a phenomenon in the literature. So we are trying to unravel why NZ is active against MRSA. So first we compare the binding energetics. The affinity of NZ214 is only slightly higher than the affinity of Plexus. So you can see this here from the delta G. The delta G is slightly more favorable for NZ as compared to Plexus. But there's a major difference for the enthalpy. The enthalpy is much more favorable for Plexus, and that means that Plexus binds to lipid 2 with more favorable hydrogen bonds and more favorable electrostatics. So that means that NZ has a more fuzzy binding mode, more fuzzy, less, more promiscuous. And that perfectly matches with the dynamics of the complex that we measure by solid state NMR. So the higher this bar, the more dynamic, the more mobile the antibiotic is in the complex. And you see the Plexus is really rigid in the complex, and NZ has a much higher mobility in the complex, which perfectly matches with the binding energetics. Keep in mind that Plexus that NZ binds lipid 2 in a much less selective manner. So if we want to visualize this, it means that Plexus forms a very specific complex, whereas NZ wiggles around lipid 2. And that could help to bind to the lipid 2 of MRSA, because the lipid 2 of MRSA is slightly different than the lipid 2 that most bacteria have. They have a so-called pentaglycine moiety at the pentapeptide, and this is work in progress. So we're trying now to understand if NZ, this higher mobility, this higher promiscuity of NZ could enable NZ to bind to the pentaglycine lipid 2, while Plexus could not bind to the pentaglycine lipid 2. But this is work in progress. So that's it. That's what I wanted to share with you. Just and we also know that NZ binds to lipid 2 in a really strikingly different manner. So let's quickly summarize this. So we know that the published binding mode is unsubstantiated. It's really different in membranes. We've identified a new interface, and we know that Plexus also oligomerizes upon lipid 2 binding. And we know that this NZ that is active against MRSA has a much more flexible binding mode than Plexus. So that's what I wanted to show. And again, thank you very much for the invitation. I'm really looking forward to our discussion. Thank you very much.
Oh, thank you. Thank you very much for your acceptation. We really appreciate your time and willingness to join us in this academic activity of our network. I think this work is an excellent example of what all of would like to be able to define of the mechanism of action that we work in the laboratories we have. We take time for questions, please. If someone like to ask Mark, let's listen to him. People.
Hello, thank you.
Hello, Laura.
If I can do a question, thank you, Carlos and Marcus, also for your presentation. I was wondering about the oligomerization of the deoxobactin, that you showed that it forms dimers, or I saw somehow a tetramer or something, but do you know actually how many monomers bind together, or how, if there is a way to know that or predict that?
That's an excellent question. The problem is that solid state NMR is a short range technique. So with solid state NMR alone, there's no way to conclude how many monomers are, or how many molecules are in a complex. This is, however, something that can be done with super resolution microscopy. So with super resolution microscopy, based on the intensity of your pixel, based on the intensity, you can obtain a distribution of molecules. That's something that we have actually already done. So my student has just recorded this data, but I'm afraid that right now I cannot answer your question. But you can do it with, you can either do it with super resolution microscopy. You can also do it with fluorescence microscopy, but you get more reliable data with the super resolution microscopy. Or you can even do it. You can also do it with cryo-EM, but in our hands, it has thus far not worked out. Yeah. All
right. Thanks for your answer.
Sorry, Marcus. Dynamic molecular simulations don't suggest some number specific?
Can you repeat your question, please?
Sorry. By dynamic molecular simulations, don't suggest some number of monomers in experiments with dynamic molecular simulation, because you present some dynamic moleculars. It's true.
Yeah.
In this, how many monomers used in this dynamic?
So yeah, that's another excellent question. So for the MD simulations, we simply used our solid state NMR structure as a starting structure. So what we put in, we get out. So you could imagine to do coarse grain simulations and then to get some distribution.
But no exactly monomer number.
No, but in our atomistic simulations, we simply use our NMR structure, and so what we put in, that's what we get out. Yeah.
More questions? Other question? People. I have one question. In vivo or in vitro, do you have competition dates for the activity of the isobactin with pyrophosphate structures in solution by competition test? Because the purpose is the pyrophosphate structures have a high affinity with the isobactin, and then if you have in solution these structures, you have competition, and maybe you reduce the activity or the clusters in the liposomes.
Is your question if it also, sorry, would bind to soluble pyrophosphate like an ADP, or is that your question?
Mm-hmm.
Yeah. Yeah, that's an excellent question. That's something that has intrigued many scientists that work on these lipid 2 binding antibiotics. So ADP or all these GDP or whatever, I mean, that's of course only in the cytosol, right? So, and these lipid 2 binding antibiotics, they only target membranes, or they only target the membranes. They do not reach the inside of human cells where you would find these ADP or molecules. The other thing is that these lipid 2 binding antibiotics, they need to oligomerize, otherwise they are not active. And in order to oligomerize, they need the tail of lipid 2. Otherwise, yeah, otherwise this couldn't work. So there are two reasons. First of all, ADP is only inside the cells, and these antibiotics, they don't go inside cells. And second, they only strongly bind to the pyrophosphate in the oligomeric state. These ADP molecules, they would not enable oligomerization. That really only it works out with lipid 2. So that's actually also the reason why they do not bind to to conventional phospholipids. So phospholipids, they have 2 lipid tails, and these 2 lipid tails would not enable these lipid 2 binding antibiotics to efficiently oligomerize, because these 2 lipid tails, they just makes the lipid molecule too big, whereas lipid 2 only has 1 lipid tail, and that's why these Tactobacter molecules can really neatly oligomerize. Not clear if I explained this well.
Yeah, it's complicated. Yeah. Anyone else who has a question for the audience?
I have some. Thank you very much for your talk. I wonder how difficult it is to do these experiments with a mixture of phospholipids. I mean, real membranes are a mix of several phospholipids, but I mean that in MR you have a lot of signals, no? So it will be difficult to interpret. But this is how difficult could be making an experiment more real to
Yeah, that's a great question. So it's a great question. So obviously, like the data that I've showed you are in highly artificial membranes. So they were all in DOPC membranes. So they're asimple, and DOPC is not even a bacterial lipid. For tioxobactin, we have done, I did not show this today for the sake of time, so we have done experiments in real bacterial membranes. Like we took membranes from Micrococcus flavus, and we also took a membrane from Staphylococcus similans. And this works out. So we actually observed major signal differences, some of which we do not understand yet. So what is really simple for us is to take arbitrary composition of lipids and then reconstitute lipid 2. That's really simple. And then we have done that. We have done for Plexus, there's actually virtually no impact on the solid state and mass spectra. So Plexus seems insensitive to the lipid composition. For tioxobactin, there's a strong sensitivity to the lipid membrane. What we can also do, we can directly take the membranes from bacteria that contain not only different lipids, but even all the different proteins or whatever. And that's more difficult, but we can do that. So that's especially something that we're investigating now for daptomycin. So we also have a major research line for daptomycin, which is highly sensitive to the lipid composition. And there it matters a lot. Yeah, it's a great question.
Hello. Hi. My question has to do with plectazine. I was wondering if the observation you made with the tyrosine and the lysine that interact with at the interface, whether it's something that is preserved amongst others alpha-beta defensins?
Most likely not, because these residues are not in these different alpha-beta defensins. So there's one important thing about the NMR data. So the fact that you observe a contact between a residue in NMR and lipid 2 does not necessarily mean that these residues interact with each other. It only means that these two residues are within 6 or 7 angstrom. Okay. So these residues do not necessarily need to interact with lipid, not necessarily strongly interact with lipid 2. And that's also corroborated by mutagenesis studies that we did. So if we replace these tyrosines by phenylalanine, the activity does not change. So there cannot be hydrogen bonds or anything. So it could be that there is that the pi or the aromatic ring is important for the interaction, but how exactly this plays a role at the interface, that's unknown to us, and we don't think it's conserved. Yeah. It also does not necessarily mean that these residues that are within 6 or 7 angstrom of lipid 2 are important because of the interaction with lipid 2. That could also be because of the oligomerization. That's something that we do not yet understand. Yeah.
Thanks.
Yeah. Someone else who has a question? I have one question. It's about the state solid experiments. In the insertion for solid state experiment is not spontaneous. Is true? How much do you have to worry about that fact?
Can you repeat the beginning of your question, please?
Yeah. The insertion for solid state experiments is not spontaneous.
Sorry, I did not understand the second word. So what? So?
The insertion for solid state experiments is spontaneous insertion.
So oligomerization? Sorry, I didn't understand. So?
Insertion in general.
The insertion. Oh, sorry.
Yeah.
Okay.
Yeah, the insertion for solid state experiments is not spontaneous. How much do you have to worry about that fact? Because when for the people no have relation with these experiments, I explain about this one. When you have the state experiments, you need a lot peptides. And the other question is, you need multilamellar vesicles. You don't have a vesicle, only one
Yeah,
layer.
Okay.
With every layer, with other layer, with other, and then for
Um,
obtain these liposomes, you need prepare the liposomes in presence of the peptide, and then the insertion is not in solution. Is not real. No? Because you have the membrane of liposome, and you have the peptide in solution, and then the peptide in solution can insertion, spontaneous insertion. But in the steady-state experiments, you have peptides in solvent solutions, and then the insertion is not spontaneous.
Yeah, that's true.
It's a general question.
Yeah,
what is your opinion about this difference in the presence of the peptide in the membrane? Is that a problem we can consider?
Yeah, that's true. So that's a potential caveat of our experiment. So I will paraphrase it. So it is true. So the way how we obtain our samples is that we co-assemble the membranes with lipid 2 and with the peptide. So that actually means that we have complexes on the outside and on the inside of the membrane, whereas in bacteria you only have them on the outside. That's a potential caveat. I agree. However, we also have done membranes with unilamellar vesicles, where we added the peptide afterwards. And so our phosphorus studies we conventionally do with unilamellar vesicles because we worried about this. And there we actually don't see a difference. But certainly for the membrane curvature or for the membrane perturbation that we observed, it plays a role if you have complexes only on the outside or on both sides of the membrane. And therefore, we actually do these experiments exclusively with unilamellar vesicles. If we study membrane perturbation, we exclusively do this with unilamellar vesicles, and we add the peptide after the formation of the complex, after the formation of the vesicles.
Okay. More questions? Someone? Okay. If next is more question. Thank you very much for your presentation. We really appreciate it.
Thank you so much. Thank you so much. Thank you very much for the invite, and I really enjoyed our discussion. Thank you.
I hope we have continuing contact for this network. I don't know if it's correct, but I invite to the research in this group entrance in contact with you for some questions or for maybe collaborations. I hope you can receive this.
With pleasure. Thank you so much.
Thank you.
Thank you.
Thank you so much for your time.
Bye.
Thank you.
Bye. Okay. Muchas gracias a todos por su asistencia al seminario. Les tengo informados para la siguiente reunión. El seminario de verdad, espero que pueda participar alguno de los colegas que no han participado. Voy a checar la lista y volveré a hacer una invitación a aquellos que por alguna razón no pudieron en su momento participar, pues que nos hagan favor de apoyarnos para el siguiente mes. Les tengo informados al respecto. Y aprovecho también para reiterarles la invitación para que hagan propuestas para hacer estancias en otros laboratorios. Entiendo que es complicado por el tema de la pandemia que estamos viviendo a nivel global, pero si ven alguna oportunidad o una circunstancia que pueda favorecer una estancia de algún estudiante, de alguna investigadora a otro laboratorio, se dan las condiciones, pues por favor no dejen de meter la solicitud para tomar el presupuesto de este año. Bueno, pues los tengo informados por correo electrónico. Muchas gracias por su asistencia.
Gracias.
Muchas gracias. Hasta luego. Gracias, Carlos.